Hello everybody, and welcome to our video on the fundamental theorem for line integrals. So here, this is I think pretty straightforward. All we're going to be doing is taking our fundamental theorem of calculus and extending it to line integration. So theorem, let C be a smooth curve given by the vector function r of t for t from a to b. Let f be a differentiable function of 2 or 3 variables whose gradient vector of f is continuous on C. Then, the integral over C of the gradient of f dotted with dr is equal to f of r of b minus f of r of a. So this effectively states that the line integral of the gradient of f is the net change in f. Additionally, the value of this integral is independent of the path taken, and only the initial and terminal points matter. Okay, so let's take a look at the proof for this. So we've got the integral over c of the gradient of f dotted with dr. We rewrite this. This is going to be the gradient of f evaluated at r of t, that's our path, dotted with r prime of t dt from a to b. Now if we take this dot product, what do we get? Well, the gradient of f should give us this df dx, df dy, df dz, and r prime of t is going to give us dx dt, dy dt, and dz dt. So when we take that dot product, this is the expression we get. And hopefully we see here that this looks exactly like the chain rule for f of r of t. So if we take the derivative with respect to t of f of r of t, we get that same thing. So the chain rule tells us that this integral is the same as the integral from a to b of d dt of f of r of t integrated with respect to t. In that case, the fundamental theorem of calculus tells us exactly that the integral of this derivative function just integrates at the endpoints of the antiderivative. That's the regular fundamental theorem of calculus. Now, we've stated this in terms of C being a smooth curve given by this vector function, but this theorem also holds for piecewise smooth curves. So that just means, like, if you've got a curve that's smooth and then has like a sharp turn, and then is smooth, but then maybe there's another sharp turn. So it's piecewise smooth because we can divide it up into finitely many pieces that are still smooth curves individually. Okay, so definition in general, if f is a continuous vector field with domain D, we say that the line integral of f dr is independent of path if the line integral over the curve C1 of f dr equals the line integral over the curve of C2 of f dot dr for any two paths C1 and C2 that have the same initial and terminal points. Okay, so fact, line integrals of conservative vector fields are independent of path. So if we know something is a conservative vector field, then we know it's independent of path. And that tells us that we'll always get the same integral values no matter what path we take, as long as the initial and terminal points are the same. Okay, so definition here, a curve is called closed if its terminal point coincides with its initial point, that is, r of b equals r of a. So here in this picture, that's what we've got here. This is our starting point, but it's also our ending point. So you go around the curve and you end up at the same spot. So another fact here, if we choose any 2 points A and B on a closed curve C, we can break it into 2 curves, C1 from A to B and C2 from B to A. And if the integral over C of f dot dr is independent of path, then the integral over this closed curve will be equal to 0. And we can see that by just splitting up our curve into two pieces. So let's just have some curve here. Let's call this our curve. So we've got 2 points, A and B, on a closed curve C. So you could have one path goes from A to B, call that C1. And another path goes from B back to A, call that C2. So then the integral over the entire curve would just be the sum of the integrals over each curve. But that would mean that if I flipped this curve around, and meaning I traveled backwards along this curve, so here we're traveling counterclockwise like usual, and then flip the other one around. So this integral should equal negative the integral over the reversed path. But if we reverse that path, we're evaluating from B to A. And so that fundamental theorem of calculus is going to give us the exact same value for these two integrals, except we're subtracting them, so they'll cancel out and give us 0. So again, that's just because C1 and negative C2 have the same initial and terminal points. Okay, so theorem. The integral over a curve C of f dot dr is independent of path in D if and only if its integral is 0 for every closed path C in D. So physically, this says that the work done by a conservative force field as it moves an object around a closed path is 0. So that's like thinking if you've got like an object and you let it fall off the table to the ground, and then you lift it back up to its original position, the effective impact that gravity has had on that object is 0. The work done by the gravity on that object is 0. Definition. D is open means that for every point P in D, there is a disk with center P in D that lies entirely in D. All right, definition. D is connected means that any 2 points in D can be joined by a path in D. So let's go ahead and draw these actually. So this first one, D is open, means that for every point P in D, there's a disk with a center P in D that lies entirely in D. So you've got some region D. So what it means to be open is that I can draw a point, and no matter where I draw that point, I can always draw a circle around it, where that whole circle is inside the region D. So if I go really close to the boundary, that's fine. I'll just have to draw a really small circle. That's the basic idea. Okay, and D is connected means that any 2 points in D can be joined by a path in D. So, for example, if I had something like this versus something like this, so if these were D, the region D, these would not be connected because you could take a point here and here, and if you tried to draw any path between them, that path is not going to stay within the region D. But over here, all of our points are connected because for any 2 points, I can just draw a curve through that region without any problem. Okay, so now that we've got those definitions under our belt, let's tackle another theorem. Suppose that F is a vector field that is continuous on an open connected region D if the integral over C of f dot dr is independent of path in D then F is a conservative vector field on D. That is, there exists a function F such that the gradient of F equals the vector field F. And finally, and this is going to be our big tool for this stuff. So hopefully, let's kind of go back through here and see what this common thread is. Okay, so what do we know? We know that if you've got a vector function F, or a function F that's differentiable of 2 or 3 variables, then you can take its gradient, and when you integrate that gradient, it gives you f of r of b minus f of r of a. But what we should ask ourselves is, if we have a gradient f, how could we find the original function f? So that's kind of what all these things that we're looking at are trying to tie together. So I know this is a lot of information at once, so that's why we're taking a moment to go back through. So if I want to apply this theorem and I only have the gradient of f, I have to be able to find this function, the original function f. So I have to be able to show that it exists first. Okay, so we're looking at this consideration. What does it mean to be independent of path? Which we know that for this differentiable function f, it is independent, its gradient is independent of f, but not all gradients necessarily would be. So, okay, what does it mean to be independent of path? It means you get the same value for the integrals between the same initial and terminal points. Okay, so we want to know what some words mean. What does closed mean? Okay, it means the beginning point ends with at the same place that the starting point began. Okay, well, what else do we know? We know that if we've got a curve that is closed, that the integral over that curve is always going to be 0, because we could break it up into 2 curves and rewrite it as the difference of 2 integrals with the same initial and terminal points. So again, but that requires that we know something is independent of path. Okay, so it's independent in path if and only if all of these integrals are equal to 0 for any closed path C and D. Okay, a couple more things. Again, now definition, D is open means that you can always find a circle around any point in the disk that's fully, or in the region D, that's fully contained inside that region. D is connected means that any 2 points in D can be joined by a path in D. Okay, and so now we get to this theorem. So some of these definitions are already into play here. Suppose F is a vector field that's continuous on an open, connected region D. So the region has to be open, meaning that for any point you pick in it, you can draw a circle around it. And the vector field has to be continuous. And the region has to be connected, meaning you can draw a line between any 2 points in the region. If the integral is independent of path in D, meaning that from any 2 points A to B in the path you get the same value for the integral, then F is a conservative vector field on D. That is, there exists a function little f such that the gradient of f is equal to the vector field of f. So now we look at this vector field of f, and we're going to write this in the form p of xy I plus q of xy j. So if we know that this is a conservative vector field where p and q have continuous first-order partial derivatives on a domain D, then throughout D, we have that dp dy, partial derivative of p with respect to y, equals dq dx, the partial derivative of q with respect to x. Now, just as a sort of side thought here, what is this saying? Okay. If this is a conservative vector field, what does that mean? That means that there exists an f such that the gradient of f equals the vector field f. Well, what does that mean? So if the gradient of f is this vector field of f, that means p is the partial derivative of f with respect to x. And q is the partial derivative of f with respect to y. So when we look at this theorem, what this theorem says is that the second derivative of f with respect to y then x equals the second derivative of f with respect to x then y. Or I should say, I did that in reverse. This one's the derivative with respect to x then y, and this one's the derivative with respect to y then x. But same point. What is this? This is just a reworking of Clairaut's theorem. That's what we're saying here. So if we know that this is a conservative vector field, we know that there's this function f that satisfies that the gradient of f is this vector field. And then Clairaut's theorem is going to guarantee that these second partial derivatives are equal. But p, that's exactly the same thing as stating dp dy equals dq dx. Okay, so hopefully this is all kind of tying together. It's a lot all at once, but if you kind of just think about how every piece is interacting, hopefully it'll make sense. So definition, a simple curve is a curve that doesn't intersect itself anywhere between its endpoints. And another definition. Okay, so let's look at these pictures first. So simple curve doesn't intersect itself. So this is simple, but not closed. This is not simple because it intersects itself. This is simple and closed because it, A, does not intersect itself, but it also encloses a region in the curve. This one is not simple, but it is closed because it encloses a region, but it does intersect itself too. Okay, so another definition. A simply connected region in the plane is a connected region D such that every simple closed curve in D encloses only points that are in D. So meaning if you draw any curve that encloses on itself that's closed, it can only enclose points that are inside D. Whereas if I draw a curve over like here that's closed, this hole in the region is enclosed by this curve, so we would say this is not simply connected. Okay, so here's the big theorem that we've been looking for that ties hopefully all of these things together. Let f be equal to pi plus qj. So f is our vector field on a open, simply connected region D. So an open, simply connected region D. Suppose that P and Q have continuous first-order derivatives and dP dy equals dQ dx. So in other words, the derivative of P with respect to y equals the derivative of Q with respect to x throughout D. Then f is conservative. What's the next conclusion? It's not part of this theorem, so this is the big thing. F is on an open, simply connected region, and P and Q, each component has continuous first-order derivatives, and the derivative of P with respect to y is equal to the derivative of Q with respect to x, so f is conservative. What does that mean? If f is conservative, that implies there exists a function little f such that the gradient of f equals this vector field f. All right, so this is the key that ties it all together. If we've got this vector field on an open, simply connected region, and its components have continuous first-order derivatives where these derivatives are equal to one another, then we can find a little f, and that's gradient is equal to our vector field f. And if we can find that f, then we can apply the theorem, the fundamental theorem of calculus for line integrals. So that's a whole lot of big ideas all in one go here. But this is how it all connects. We want to be able to apply this fundamental theorem for line integrals. In order to do that, we have to be able to figure out what f is, starting with our vector field. But that means we need to know that the vector field we have is conservative so that we know that such an f exists. And this theorem that ties all that previous information together gives us our way of determining if such a function exists. So, example 1. Determine whether or not f is a conservative vector field. If it is, find a function f such that the vector field of f equals the gradient of little f. Well, the first thing we're going to check is this is p, this is q. So what's dq dx? Well, that's going to be 4y. And what's dp dy? That's going to be negative 4y. So dq dx is not equal to dp dy, which implies f is not conservative. And since f is not conservative, we won't be able to find a little f. So we won't be able to apply the fundamental theorem of calculus here. Okay, well, lame, but at least we know we won't be able to use that to evaluate any such integrals of that type here. But we could use our direct methods. So let's move on to another example. Example 2, if f of xy is 3 plus 2xy I plus x squared minus 3y squared j, find a function f such that f equals the gradient of little f. And then here we've got this other question, evaluate the line integral of f dr. So the same f, but here we're specifying that we want to integrate this thing over this vector curve r of t. Okay, so let's start with part A here. Find a function f. Well, let's first make sure that such a function exists. So again, remember this is p, this is q. So what is dp dy? Now, if you get confused on which one you take the derivative with respect to y and which one you take the derivative with respect to q, try to come back to the fact that, hey, if this function exists, this is the partial derivative with respect to x, and this one would be the partial derivative with respect to y. So I got to take the derivative with respect to the other variable and check if the combination is equal. So this is going to give us 2x here. And dq dx is also going to give us 2x, so that's good. Now, how do we find such a function? Well, actually, what we just wrote up here is the big hint, right? So f, this p is the derivative of f with respect to x. So f needs to be the integral of p with respect to x. Now, of course, when we integrate, we should have a constant of integration, but there's something a little tricky here because we're talking about a function of two variables. So here, when I'm integrating with respect to x, anything that's a function of y would be treated as a constant here. So when I add my constant of integration, it actually needs to be an entire function. So I'm going to call that function g of y here. Now, likewise, f needs to be equal to the integral of q with respect to y. And here, since we're integrating with respect to y, our constant of integration actually needs to be a function of x. Now, f needs to be equal to both of these things, right? But keep in mind, first of all, we're finding a function f such that the vector field of f equals the gradient of this little f. So it specifies find a function. There technically could be infinitely many such functions because they could all differ by a constant here. But what we really are just trying to do is just match up the information we have. So we know, hey, here we're missing some function of y, here we're missing some function of x. So let's just combine all this information together. What do we got? Well, this thing should look like 3x plus x squared y. And then it also needs to have, well, here we've got the x squared y already taken care of. So don't include it twice. It only needs to be included the one time. It's the same here. And then here we've got minus y cubed, which was missing from this function. So minus y cubed. And again, my g of y is the minus y cubed. That's the missing y function here. And my h of x is the 3x. That's the missing x function from this part. Now I could put plus c here, but I don't need that. I'm going to be using this for the fundamental theorem of calculus, and it didn't say find all functions. It said find a function. So we don't need to worry about tacking on a constant at this stage. Okay, so there's my little f of x. So now let's tackle part b. So we want to integrate over c of f dot dr. But we know that this is equal to little f of r of, in this case, our endpoint for our curve is pi, at pi, minus f r of 0. So let's evaluate those. R of pi is, what do we get here? E to the pi times sine of pi, which is 0. And for the y-coordinate here, it'd be e to the pi times cosine of pi, which is negative 1. So this is negative e to the pi. And r evaluated at 0 is, well, e to the 0 times sine of 0, which is 0. And for the y-coordinate, we get e to the 0 times cosine of 0, which is 1. So e to the 0 is 1, so this is just 1. So in other words, this can be rewritten as f of 0 negative e to the pi minus f of 0, 1. And now we can just plug that into our function. So that's, I think that's pretty nice. I truly think that is far easier than most line integral problems. So what do we get here? 3 times 0 plus 0 squared times y, which is negative e to the pi, minus negative e to the pi cubed, minus f of 0, 1, which is going to be 3 times 0 plus 0 squared times 1 minus 1 cubed. That's 0 plus 0 minus a negative e to the 3 pi, but that becomes a positive e to the 3 pi. And this is minus negative 1, which is plus 1. All right, that's it for that question. So let's go ahead and move on. Okay, if the vector field f of xyz equals y squared I plus 2xy plus e to the 3zj plus 3y e to the 3zk, find a function f such that the gradient of f equals cap f, the vector field. Well, the process is going to be exactly the same here, but keep in mind that now this is little f of f sub x, the partial derivative with respect to x. This is the partial derivative with respect to y, and this is with respect to z. So we could check here. I'm not going to check this time. I'm just going to tell you outright such a function exists. I'm going to skip that step on this problem just to save a little bit of time. So let's go ahead and try to find our function f. So f equals the integral of this y squared with respect to x, which gives me xy squared plus. Now in this case, both y and z are being treated as constants. So my constant function here is going to be g of yz. Now we're going to integrate this with respect to y. This becomes xy squared plus y e to the 3z plus, and now this is going to be a function of x and z. And finally, we'll integrate our last term with respect to z. This gives us y e to the 3z. I would have needed to do u substitution, but I would have divided by 3 and canceled that 3 there. Plus some function, let's call it, I don't know, v of x and y. Now again, we can put together a function that satisfies all of our needs by just taking the components. Okay, that one's covered xy squared. It appears in both of those. So we've got that. Plus, now what do we got? Well, we've got y e to the 3z appears in both of those functions. And that's it. That covers all the functions that appear in every version of these integrals. And again, I could put plus a regular constant here, but it doesn't ask me to find all functions. It asks me to find a function. This one works. And if you want to double check, you could always check that it works by just taking the gradient here and making sure that you get the same 3 values. Okay, so conservation of energy. So Newton's second law of motion states that force equals mass times acceleration. So in other words, the force along a path or at a point in the path is equal to the mass times the acceleration of that curve at that moment. So this implies that the work done by the force on the object, which is, as we've seen, the integral over c of f dot dr, can be written as the integral from a to b of m times r double prime of t dot r prime of t dt. This is equal to the mass divided by 2 of the derivative with respect to t of r prime dot r prime of t dt. So this is something we saw way back before in the dot product derivative rules. But this just comes down to, since you're taking the dot product of r prime and r prime, when you take your product rule for your derivative, you end up getting 2 of these things, right? But since we started with only one of them, when we go in this direction, we get half. So we're just compensating by dividing by 2. Okay, well, we also know that the dot product of r prime with itself is the magnitude of r prime squared. So we're looking at the derivative with respect to t of the magnitude of r prime squared. Now, when we integrate this, what are we going to see? Well, we're integrating the derivative with respect to t, so we just get that function back. So this becomes the mass divided by 2 times the magnitude of r prime of t squared evaluated from a to b, which looks like this: m over 2 times the magnitude of r prime of b squared minus the magnitude of r prime of a squared. Therefore, the velocity, setting velocity equal to r prime of t, right, just notationally, gives us the following law, that work equals 1/2 the mass times the velocity of b, the magnitude of the velocity of b squared, minus 1/2 the mass times the magnitude of the velocity at a squared. All right, so that's basically just a result from Newton's second law of motion. Up to this point, now we have a name for this thing, this expression in particular in terms of t. K equals 1/2 the mass times the magnitude of v of t squared is called the kinetic energy of the object. So if we rewrite this calculation we just did for work, what we've shown is this physics law that work is equal to K of B minus K of A, which states that the work done by the force field along the curve C is equal to the change in kinetic energy at the endpoints of C. Okay, so let's move on. In physics, so another example here to look at is that in physics, the potential energy of an object at the point xyz is defined as P of xyz equals negative F of xyz. So in other words, the vector field F is equal to negative the gradient of the vector field P. So the work here, we've got F dot dr equals negative the gradient of P dot dr, which equals negative P of R of B minus P of R of A, which equals P of A minus P of B. So where A and B are the endpoints. Okay, so what does this give us? So work is equal to P of A minus P of B, and work is equal to K of B minus K of A. So if you set those two things equal to one another and rearrange them slightly, you get P of A plus K of A equals P of B plus K of B. So the potential energy plus the kinetic energy at the start is always equal to the potential energy plus the kinetic energy at the end of the point of movement. So that's what we call the law of conservation of energy. All right, so just to tie that all back together, Newton's second law of motion gives us force equals mass times acceleration. We do a little computation on the work here. And from this formula, we can look at the kinetic energy of an object, which is something we get from physics, this law, and see that work is the difference between the kinetic energy at the start and the end of a path. And likewise, looking at potential energy, work is the difference between the potential energy at the start and the end of the path. And then setting those two versions of work equal to one another gives us this law of conservation of energy. All right, so hopefully that's a little bit of an interesting expansion on these ideas for line integrals. That's going to be it for this video. Thank you for watching.